Our project for assignment 2 is to create an artist classification. This project is done by Jai and Deshna.
For our assignment 2, we decided on creating a convolution neural network that could predict the artists associated with a given artwork. We chose this particular model because we have not tried image processing in this class, and we were interested in learning more. We found a dataset on Kaggle that contained 50 different prominent Western artists, and we had the goal of creating a model that could map the correct artwork to each respective artist.
Right off the bat, we noticed multiple different components of this dataset that may cause us problems. Our dataset was extremely skewed. Printing out a visualization of our data shows that the curve of our dataset resembled a logarithmic curve. The first three were prominent, but even they vary significantly. For example, Vincent van Gogh had well over 800 artworks stored within this dataset. Second in line is Edgar Degas with about 700 artworks. Third is Pablo Pascal with a little over 400 pieces of artworks. Just from the first three classifications, it varies by hundreds of data points. The artist with the least amount of artwork in the dataset has only approximately 20 pieces. This extremely skewed dataset immediately raised alarm that the model may overfit to the dominant classification, and while it may appear to have a high accuracy rate, it's just guessing the more prominent classifications rather than learning for all the classes.
To combat this, we decided on visualizing our model results with a confusion matrix. A confusion matrix places the true label and predicted label on adjacent sides of a table and compares the model's guesses with the actual results to visualize how accurate the model actually is. We will be using a confusion matrix to assess the validity of our model's performances and evaluate how well our model is at predicting with accuracy which artworks belong to which artist. A very basic baseline for our model would have just started at wanting it to score better than a shot in the dark guess. However, our skewed dataset presented some complications. If the dataset was even throughout all classifications, then anything consisting better than a 1 out of 50 would show that our model has at least learned something. However, the sheer variation in data points per classification makes this much harder. Knowing the complications of our dataset, we aim to still do our best and have a majority accuracy rate at around 70%.
Taking our dataset, we processed it the best we could. This dataset consists of three parts: images, which contains the folders of the 50 artists and their respective arts and size; resized images, folders with all the art files; and a CSV file with information about the artists, such as the artist's name, year, birth, death, art movements, nationality, a short bio, a Wikipedia page, and the number of paintings from that particular artist. In total, there are about 8,355 images in the dataset. The image of the artwork in a JPEG format will act as the input to our CNN, and the output will protect the name of the artist who created the artwork. This means we will only be using one column, the artist's name from artist.csv. We will match the images based on which folder they come from, and the image is part of the dataset and connected to the artist's name. Again, there is a class imbalance since the number of artworks per artist varies. We will address this using techniques such as data augmentation and weighted loss functions.
As convolution neural networks are known for being suitable for image processing, we both spent a substantial time studying and understanding the concept behind this model. Through our studying, we found that many image processing models also utilize a technique called image augmentation. Augmentation techniques allow the model to also be able to process an image that might not be oriented the same way as others. In our dataset scenario, it would be like taking a picture of a painting in a museum and feeding it to the model to have it predict the artist. However, because the picture is skewed, the lighting is a little off, and the image is a bit blurry, the model performs especially poorly. Image augmentation takes that into account and augments some images to have a color jitter, rotation, and more to prepare the model to also take images that aren't in the ideal conditions.
While our dataset mostly contains images with correct orientation and color, we really wanted to make a model that could one day take in a piece of artwork we are curious about and be able to tell us the artist. For the data augmentation, we referenced the Torch documentation and we chose Gaussian blur, flips, offline, color distortion, and crop, as we believe those components would be the most appropriate for our dataset. Given that our dataset involved images of artworks, we believe that augmentations like warping wouldn't be particularly useful. However, Gaussian blur was chosen in the case of blurry photos, flips were chosen in the case of image flips, offline was chosen in the case of skewed images, color distortion could occur depending on camera or even lighting, and cropping can vary from photo to photo. We hoped by putting these augmentations in place, they would make the model more robust against these possibilities.
Diving deeper into visual inspection, the dataset consists of a diverse range of artistic styles, from highly detailed realism to abstract and minimalist artworks. Firstly, the dataset was split into two folders, images and resized. After we downloaded, there were some duplicate folders and images. We deleted it, and all the duplicate images linked to it in resized. Images folder has another images folder in it, so we just removed the one extra step and got the artist folders out. Now, regarding the paintings, some paintings have high contrast and distinct color palettes, which may make classification easier, while others, more specifically the black and white sketches or heavily stylized pieces, may be more difficult to distinguish. Additionally, variations in image quality and resolutions could impact model performance, as some images appear pixelated or resized in a way that distorts fine details. Another factor to consider is class imbalance, as some artists may have significantly more images than others, causing the model to become biased toward predicting those more frequently.
To lessen the effect of the skew, we decided to cap all artists at 300 pieces max, which created a much smoother slope of data variation. Additionally, evaluating confidence scores across different styles can further reveal which categories the model struggles with most, guiding further refinements in training. Implementing these improvements will enhance the model's ability to generalize across a wide range of artistic styles, making it more effective in classification tasks. Besides the image data, the dataset also contained artist information in artist.csv, which we refined by performing several preprocessing steps. First, we were planning to remove any null values using drop.na and duplicate entries with drop duplicates to reduce redundancy and impact on the dataset. However, we realized that there were no null values or duplicates in the dataset. After that, we removed unnecessary columns such as bio and Wikipedia, which were not directly relevant to our analysis. There were other categorical features within the CSV, such as years and nationality, which were interesting, but we deemed it not particularly relevant to our model at the moment.
We began with a model consisting of 3 convolution layers with increasing filter sizes 64, 128, 256, followed by max pooling layers to reduce dimensionality. Fully connected layers were used at the final stage, with the last layer corresponding to the number of artists in the dataset. We applied ReLU activation across all layers to introduce nonlinearity, and the model was trained using the Atom Optimizer with a learning rate of 0.001 and a cross-entropy loss function, all of which is also standard for multi-class classification tasks. Training was conducted using a batch size of 32/15 epochs, which took exceedingly long to process.
We created a custom PyTorch dataset class, called Class Art Dataset, to load and process these images. Each image was converted to RGB format, assigned a label based on its artist, and stored accordingly in a list. We resized images to 224 by 224, as that is the standard for CNN input, applying data augmentation techniques such as random cropping, rotation, color jitter, horizontal flipping, and Gaussian blurring, all of which we believe are reasonable distortions our CNN may experience in the real world. We also normalized the images using ImageNet's mean and standard deviation values. The dataset was then split into an 80-20 ratio for training and testing for the total images for each artist individually. Since the output from our model was 50 values, we made it so that our label would be torch.long to match dimensions so the model could calculate the loss between the two. During our first iteration testing, the model achieved an accuracy of about 29%, which is significantly lower than our goal. Several factors could have contributed to this result. Class imbalance definitely affected training, even though we tried to offset that by capping the top 3 artists at 300 examples each. The complexity of the task itself was another factor. Artist classification could be challenging due to the diversity of styles, even within the same artist body of work. Additionally, different artists could share different styles or subjects, especially if they're from the same artistic era. Finally, training for only 15 epochs might not have been enough for the model to learn meaningful artistic patterns. Overall, our model is most likely underfitting and needs more training on a more robust architecture. Over here, we have an image of a confusion matrix of the artist classifier. For a confusion matrix to show that the model is doing well, ideally you'll have a horizontal line going down the side, where the model's predictions align with the true label. However, as you can see, there is no pattern or no horizontal line being made, showing that our model is not doing particularly well.
To improve performance, we did want to extend training 50 to 100 epochs to allow the model more time to learn. However, the processing time for training over that many images made it incredibly difficult to accomplish. Additionally, we decided that printing out both training and testing accuracy rather than just testing accuracy could have been helpful in determining that our model has simply not learned enough earlier on. We also explored more advanced architecture due to the complexity of our dataset. We stuck with what was standard, for example, the learning rate, but it may not have been what was ideal for our model, and perhaps pushing things a bit could have improved performance. Addressing class imbalance through weighted loss functions or oversampling underrepresented classes might help stabilize learning. Through our research, we learned of the SMOTE function, which could artificially boost classes with not enough data points to try and even things out. Unfortunately, we were not able to successfully implement that in our code, though it could be something that could be beneficial in evening out our data set further. We also spent quite a bit of time tuning the hyperparameters and testing what worked better and what didn't. A 29% accuracy is still higher than the 2% if it was just guessing, but it was clear we needed further optimization to achieve higher accuracy. Image classification models in datasets like this are quite common, such as basic cat-dog classifier. Image classification models also have great applications, such as cancer cell detection, computer vision for self-driving cars, and more. Looking at the Kaggle postings of this dataset, it seems like many others were able to accomplish a much more robust and accurate model that can successfully identify a piece of artwork to its artist. Real-life applications of a dataset like this could help categorize artworks in museums or be a program for users to find more information about an artwork they're interested in, like a visual version of Shazam. We hope to circle back to this project in the future and improve our model into a much more accurate program.